Hello, I'm Lindsay Gold from the University of Dayton in Dayton, Ohio, and I am here with my partner, Johnny Ashurst, and I'll let him introduce himself.
Hello, I'm Johnny Ashurst. I'm from Harlan, Kentucky. Glad to be here.
Thank you. Tonight we are going to talk about measurement, specifically measuring angles, shapes, lengths of objects, perimeter, area, volume, all kinds of things, and how these concepts span across the grade levels from kindergarten through grade 12. I'm going to be doing the elementary part, and then Johnny's going to be interjecting with the middle and high school part. And the technology that I'm going to be using is the TI-Nspire CX app for iPad. And then Johnny's going to be using the TI-Nspire CX Premium Teacher software. So we're going to start by sharing my screen here. So I will do that real quick. And hopefully then you are seeing a blank geometry page. This is a geometry page. And so the first thing that I would do if I were using this with students is I would go to what is the settings icon. You'll see like home and add, and below those you'll see a wrench, and then 3 lines with 3 dots, and then what looks like a gear, and that's our setting. And you want to make sure that you are forcing the geometric triangle angles to integers and automatically labeling points. So that is something that I had done beforehand, but that would be one thing to do here before you get started. So then you can just tap OK. So we're going to start by creating or constructing a triangle. So if I hit the little wrench tool here and I go to shapes and triangle, and Johnny, how many points are in a triangle, or how many vertices in a triangle?
3.
So I'm going to tap in 3 spaces. And as you can see, they have already labeled my points for me, which is really nice. I can move my letters a little bit for my labels for those points. And then I want to measure the angles. So to do that, I'm going to go back to my wrench, and I'm going to click the back button for tools, and then go to measurement and angle. And if I want to measure angle A, I need to make sure that that comes in the middle of my tapping. So I'm going to tap on B, A, C. And you'll see that they gave us 58 degrees to measure that angle. And then to measure B and C, I'll do the same thing. So we have our wrench, angle, A, B, C to do angle B, and then wrench, angle, B, C, A to do angle C. So Johnny, what do you notice about those angle measurements?
Well, they're pretty close, but they're to each other, but they're all different.
They all are different, and you could even, grab one of those points and move them if you wanted them to be. Ooh, look at that! I had 2 of them the same that time. You can move them around to make them more different, or whatever here. But in this case, yes, there are 3 angles, 3 sides, which make the triangle. But all the angles are measuring different. I would like to try another shape, so I'm going to go to my second geometry page, and this time I want to make a rectangle. So to do that, I'm going to click on the wrench, shapes, rectangle. And Johnny, how many points or how many vertices in a rectangle?
4.
But with this, you actually only need to tap 1, 2, 3 times, and your rectangle is created, because the first 2 taps are defining your length, and then that 3rd tap is your width, and then it fills in the last side there for you. So now let's look at the measurement of a rectangle. So I would talk to my students. This time we're measuring 4 angles. So I'm going to go to the wrench, and I'm going to go back to measurement and angle. And if I want to measure angle A, I need to make sure that's in the middle. So I'm going to hit D, A, B, and we see, oh, that's 90 degrees. Well, let's look at B. We'll measure angle B. So we have A, B, C. That's another 90 degrees.
Yeah.
Johnny, do you have a guess what C might be?
I think it's going to be 90 just because it looks like it's a right angle. And it looks like it's based on the ones you've already done. So I'm guessing 90.
I think you are right. And the students then can measure those angles, make those guesses, and then check themselves. So here you'll see that all 4 of those angles are measuring 90 degrees. And how is that different from the triangle, Johnny?
Well, it looks like here you don't have any choice. They're going to be 90. And with the triangle, you move things around so you could make those angles sort of what you want.
Exactly. So I moved it around a little bit and those angles didn't change. Whereas before with the triangle, you're right. When I moved the point, the angle changed. So let's talk about, these are polygons, right? Do you agree with that? So let's go to another geometry page. Johnny, what's the difference between a polygon and a regular polygon?
A regular polygon would say to us, or that we would know that all the sides would be the same measure, and a regular polygon is convex, not concave, and all the angles would be congruent or the same.
All right, now I trust you. You've been teaching a while, but let's check it out anyways. So if you go to the tools and you go to shapes, this time we're going to choose regular polygon. And if I want to make a triangle, I'm going to tap once to make a point, tap twice to make another point, and then tap a third time, but instead of just a tap, I'm going to do a tap and hold. And if I then move, whoops, we're going to reverse that. Let's try that one more time. A regular polygon, we have a tap, and a tap and hold. There we go. And then if I move my finger clockwise, that changes how many sides are in my regular polygon. So in this case, we have a triangle. So we have our 3 sides and 3 angles. And then you mentioned that the angles would be the same. Is that correct?
Right. Yes.
Okay, well, we're gonna double check just to make sure. So we have a 60 and tools, angle, and let's see what B is. We have another 60. It's
Right.
looking good. Angle, and C is also 60. But you mentioned something else about a regular polygon.
All the sides should be the same length.
Okay, to measure a
They
side.
will be.
Okay, let's check it out. To measure side, you click the wrench again. And then this time we're going to click length. And I want to measure line segment CA. Well, look at that. And it popped up there for us. Let's try another one. Length of AB. Oh, it's looking good for you.
Yes.
Length of BC. Awesome. So then the students can explore those and see with the triangle in this case that they're the same. They can move the points again. Mm-hmm. And Johnny, what's changing when I move one of those points? What changed?
It's dilating. It's getting larger or smaller, but the relationship of all the angles doesn't change. The relationship of the sides, that relationship does not change.
I love that mathematical vocabulary. Awesome. Okay, I want to try and I want to make another regular shape. So I'm going to shapes, regular polygon. Okay. This time I'm going to tap, tap, tap and hold. This time I'm going to make this shape. This is a rectangle, right?
It is.
Okay, so will it hold true that all these angles will be the same?
Because you called it or started with it being regular, yes, all the angles would have to be the same.
All right. Now, what did we say about the angles of the rectangle on the previous page?
The angles
What
were
did they
all,
measure to?
the angles were all 90 there also.
All right, so let's check it out. Here, I'm seeing all 90. And now we're going to measure a side length. So GD, all right. So can we take a guess that DE will be similar?
Yes, all
So
sides
that,
are the same.
okay, so if you know those, and we're pretty confident that the other two are the same. Johnny, what's different between this regular polygon and the rectangle from our previous page?
That original one was a polygon that was a rectangle, and this one's a polygon regular, a rectangle, but since it's a regular, it's a square.
Exactly. And the students could, once again, they could change, you know, the side lengths and those kinds of things, but they could explore with the square.
Yes.
I want to do one more regular polygon. So I'm going to go back to shapes in regular polygon and do my tap, tap, hold. And this time I'm going to make this. Johnny, what is that?
That's a pentagon.
Right, because what makes it a pentagon?
5 sides in a closed polygon.
Excellent.
Well, figure, or it would not be a polygon.
Thank you. So we're going to measure one of these angles. And then I'm going to pick another one just to make sure. So is it safe to say that all of those angles will measure to be the same?
Because you started with that being a regular polygon, yes, they will all be the same. So I trust that you have 108 degrees at every vertex.
I agree. Now let's measure a side length here just so we know how many or what length each one of those sides are. So we're pretty confident that all those will be the same as well, right?
Yes.
Okay, so we learned the triangle, each angle was 60 degrees, and the square, each angle was 90 degrees, and the pentagon, each angle was 108 degrees. So what I would do with the students next is I would create a spreadsheet page for the students to look. Here we have, you can see at the top with the capital A, B, and so on, we have shapes, sides, angles, degrees, and total degrees. So under the shapes, I have triangle, square, pentagon. And for a triangle, it has 3 sides, 3 angles, each angle measuring 60 degrees. And then for a square, we have 4 sides, 4 angles, each measuring 90, and a pentagon, 5 sides, 5 angles, each measuring 108. Now I want to know how many total degrees are in each one of these shapes. So to fill that in, I'm going to click right below total degrees, and I'm going to double click to bring up the keyboard, and I'm going to look for an equal sign. Whoops, I just lost the keyboard. And
Pardon me.
No, go ahead.
When you did the double click, you did put your equal sign in. So
I did. You're right. You're right. So thank you for noticing that. We'll get rid of one of those because we really don't need to. Okay, so we have our equal sign, and now I want to multiply the number of angles by the degrees of each angle. So I'm going to click on VAR for variable, and I'm going to choose angles, and then I'm going to choose times VAR degrees, and I'm going to hit enter, and then that'll list then how many total degrees are in each one of these polygons, regular polygons, or polygons in general. All right, so from this, Johnny, I want you to take us another step forward. So I'm going to stop broadcasting and I'm going to send it back to you.
And let me do the same thing here, do a share. And I'm going to share my TI-Nspire page. And if you can see that, I'll be happy.
Yes, we can see that.
So since you were talking about angles, I've decided to back up just a little bit and duplicate a couple of things so that it will seam together. Because what you were doing, talking about the angles and showing us how to measure, I have created an angle by placing a ray on the screen and another ray, and those rays have a common starting point. I've labeled this angle as A, O, B, with O being at the vertex. And if we like, we can go ahead and do an angle measurement. And I'm going to do 2 angle measurements here. And I'm going to click on A, O, and B. And I've created or calculated or measured, I should say, the angle AOB. At the same time, I'm going to measure one more time and use directed angle. And I'll click on A, O, and B. And of course, those 2 values are the same, as we would expect. The difference is that when I grab B, or array OB, and expand or open the angle, you'll see those values are still the same. And when we get down to what I would call a line, 180 degrees. So 180 degrees is something we're going to talk about in a moment, but I want to go a bit further, because as soon as I go further, you'll notice that the directed angle continues to measure in that counterclockwise direction, while the angle measurement seeks out the smaller of the 2 choices. So I'm going to continue around, and the angle measurement is getting smaller, while the directed angle is getting larger. And if I'm able to, that's really close. I'll get to 360 degrees. And if I move beyond that, we simply start again. So what I'm thinking about here is this. The important part of this angle, it's important to know that we have this measurement and angle measurement and directed angle measurement. So I want to go just a step further and take this idea to a fresh screen where I'm going to insert a line. And on that line, I'm going to place a couple of points. And those points I'm going to label A and B. So I've got a question for you. Would you mind if I place a ray where its starting point is simply between A and B? So are you okay with that?
I am. That looks great.
Okay. Now, this looks very much, and I'm going to go back to this page. It looks very similar to this, with the exception that I have this ray. So what's going on here is that I've extended that side, and I've done that simply by putting a line on the screen. And this ray C, and let's call that, we need a point there. And that's CD. So CD has broken the AB line into two angles. Now, I don't know what this angle is, and I don't know this one, but I do know this. If I make one of them larger, the other seems to be smaller. Well, I'm going to try one more thing by doing this. I'm going to leave that, and I'm going to do an unusual angle. I'd like to put another line on the screen, and I'm going to do that right here. And I'm going to once again place points on that line, and I'll use now, here's the challenge. I'd like to create an angle on that new line, GFE. And I'd like for angle F, or position F, to be the vertex of this angle. Now, for some students, they'll look at me like, why are you even doing this? It is what they call a straight line, or what we call a line. So I'm going to measure the angle that starts with E, F, G. And we've done that for one reason, to see that the line has a 180-degree angle if all 3 points are collinear and on that line. So we're going to use that fact and to go back up to this diagram and to know that the angle ACD and the angle DCB are two angles that would add together to be 180. That's essential for where we're going. Comments, or can I go forward?
I think that is wonderful. Keep going.
All right, so here's an example. And what I like about this example I presented is that immediately the students look at those numbers and do you see an issue?
Well, you just told me that a line was 180 degrees, and I don't think if I add those together, I get exactly 180 degrees.
Beautiful. That's what I need for students to say, because right now we're dealing with two issues. Issue one, mathematics. Issue number two, technology. So I'm going to right click on the screen and choose text and create M plus N. And all that means is there's a sample of, I'd like to add two things together. And that's very generic. But if I right click on that and choose calculate, this says, how about giving me a number for M? Well, I'm going to click on this number. Then on screen, I'm asked to select a number for N, and I'll choose this value. And I'm going to place that result right here. It was 180 degrees, even though, I'm going to give what I consider to be a reasonable statement. The two angles of 110 and what I see as 69.7 is really 70 degrees, so that we have a 180 degree. It's possible that it's really 69.7 and the 110 was rounded off, because what we're dealing with in technology is rounded off decimal places in the settings. However, TI-Nspire measures the angles precisely. It only displays a rounded off value. So when we dealt with m plus n, we get 180 degrees. And again, that's essential for where we're going. And let's test that theory. As I move B, I'll move, stop. That's 180 degrees. 180 degrees. Ooh, oh, that one's nice. Does that mean that was actually 29 and 151? Those are two rounded off figures that just show up very nicely. So the thing that I want us to think about is if we have a line and we break it with a ray, there's two angles. And right now, I'm going to show you something that just makes no sense at all. 3 lines. And without any measurements inserted in those, I'm going to manipulate those . Same thing we had before, but I now can see that I could create with these 3 lines a closed figure called a triangle, similar to what you're doing, but in a different manner. Now, with the line that's highlighted right now, you'll notice that it has been broken by another line, and my cursor is on the left and on the right. Those two angles together have to add up to be
180.
Likewise, this line, and I'll change its appearance slightly. That line has been broken into with 2 angles here. And I don't know the 2 angles, but I know the sum of their degrees is 180. And likewise here, 180. Now, let's think about that and put some measurements there. On this screen, you'll see that I have 2 angles, but one of those, the 48.1, is inside the triangle, and the 132 is exterior to the triangle. We have 65.9 degrees interior angle, and its matching exterior angle is 114 on the screen. Keep in mind when I say matching, I'm speaking of a supplementary angle. Those two together will make a total of 180. And the third location, we have 66 degrees inside and 114 as the exterior angle. Now, here's a question, Lindsay, because you did it earlier. If we add the 3 angles inside the triangle, how many degrees should that be?
It should be 180.
So I'm going to create another generic arithmetic. Because I've got 3 vertices, I'd like to do some calculation. So this is generic, and we can click on it and choose calculate. And now I'm asked to find a value for m. I'll choose this first interior angle, the second interior angle, and the third interior angle. And I have 180 degrees inside the triangle. Well, I'm going to go right back to this generic m plus n plus p and calculate, but this time using the exterior angles. Interior angles total 180. We knew that. But the exterior angles is 360 total. Now here's why I think that makes sense. 180 and 360, that's the same as 3 180s. And we have 180 degrees here, 180 degrees here, and 180 degrees here. And if I could very inappropriately talk about Newton's laws, we have conservation of angular measurements here, and we just added them in 2 groups. So the 180 is just as you'd confirm, that's the interior of the triangle. The 360, well, that's the exterior. Well, you caused me to think, well, what would happen if I didn't use a triangle? In other words, what if I didn't use 3 lines and compose a triangle? So I looked ahead. Now, before I look ahead, I'm going to stop and say this. You have a triangle, and the way I extended each one of those was to create a ray. So that ray starts at C, passes through A, and out beyond D. And we did a ray with each one. So we create one extra ray to have an external angle. And you can see right here, we know that that will be 130 because it's a supplement of 50. And that's 90, we expect 90 here. If that's 40, this would be 140 because we have supplements. More importantly, we have 3 lines that have come together in this pattern. So let's look ahead and briefly, what about this 4-sided figure? This quadrilateral, and I've already measured the angles inside and the angles that are exterior, meaning the angle is created at that vertex from this side and the extension of the other side. Now, this surprised me. I wanted to quickly add the angles together, get a sum of the angles inside and those outside. So I've gone ahead and created a generic A plus B plus C plus D. Once again, we'll use that to calculate. And I'm going to calculate or total the interior angles. That's a 4-sided figure, and I think you did that before.
Yes, we did. We looked at a rectangle and a square. Mm-hmm.
And that rectangle and square, those had 90-degree angles, and 4 of those is 360. I don't have such a nice thing, but I do see this. The total of those is 360. And if I move things around, that total isn't changing. Well, I'm going to now measure the angles or some of the angles outside. All right, Lindsay, this is a trick question. Okay. The last time the angles outside the polygon totaled 360. This time, and I'm really not going to give you a chance to answer. Not what I expected. 360 degrees is the total of the interior. 360 degrees is the total of the exterior. With the triangle, we had 180 inside, interior, and still 360 outside. And here's why. This quadrilateral, this 4-sided shape, really comes together with 4 lines that match up or intersect it to create this closed figure. That gives us 4 places where we consider, I've got 180 degrees to deal with. There's 180, here's 180, there's 1, and there's 1. Collectively, we have 720 degrees. And the inside took half of that, and the outside is 360 still. Well, I just decided to go crazy and look at one more example. Well, look at that one. I now have one of those pentagons you mentioned. In this pentagon, I have, let's see, what do we have here on, I think I've already got those measured. If you can see those, I did the, whoa, the angles inside totaled 540. Now there's a quick way to do that. It's add up all those just like we'd been doing, but I also broke that pentagon into 3 triangles because I remember each triangle is 180 degrees, and 3 times 180 degrees gives us 540 degrees. This part would surprise us. Still, the outside angles, the exterior angles sum 360 degrees. I find that to be remarkable in a way, and yet not, because we have 5 sets of supplementary angles. Well, that's 5 times 180. That's 900 degrees. And if you total the outside and the inside here, we're going to come up with 900 degrees. And I want to generalize by doing this. Now I've got an octagon. And the measure of the interior degrees, I didn't even measure. I simply marked triangles, and I have 1, 2, 3, 4, 5, 6 triangles inside of this octagon. Well, 6 times 180, that's 1,080. And now there's a formula that teachers give, and they maybe not always explain it because of time, and it's n minus 2 times 180. Well, if this has 8 sides, and if I insert n as the value 8, I also get 1,080. But here's the strange thing. What if we add up all of the degrees in the exterior angles? Well, I've got it highlighted. The more lines that we insert into this, the more it's going to change our interior, but yet each of those vertices is created by a straight line that had a ray in it, breaking it into 2 pieces. At each one of those, we have nothing more than supplementary angles. One inside the triangle, the supplement is exterior. And because of that, always those exterior angles will total 360 degrees. And when we only look at a rule, we don't quite see that always. When we project in this manner and give students a chance to see the pattern and why that works, I think that's powerful. So, Lindsay, can we move on to area and perimeter?
Sure, absolutely. I really like what you did there, making the triangles within this shape. I think that is really cool. And you are, or at least I am, more apt to remember a formula if I understand why. So thank you for doing that. I'm going to go back to sharing my screen. And that will happen here in just a second. And this is where we left off before, but now I want to go to a new problem. So over here, Johnny, tell me, what do you see here? That's what I would ask my students first. Before I said anything, what do you see on this screen?
Okay, I like that question because for me, I always like, before students do anything, I want them to assess what's available, sort of like even a crime show. See the evidence that's presented. So I see a grid with a 1 unit square already highlighted, and I see a slider that can change the length and one to change the width, and I also see the perimeter is posted.
Okay, so the U, talk to me about the U.
Well, the U says to me that I don't know if you're measuring in feet, miles, millimeters, but since I can't see a measurement, I'm going to assume, or not assume, but we're going to use U for unit as generic labeling of whatever we've used to measure with. We might have measured with paper clips. So, and the fact that we're using a U in both length and width so that we're dealing with units to have the same, we wouldn't be dealing with feet in one and inches or yards in the other.
Exactly. And so I would talk to my students about that, and we would start exploring using the length slider. Check this out. If I change the length to 2, what did that do to the perimeter? So you might not have saw it. So look at the perimeter. I'll go back to 1, and now I'm going to 2. Johnny, what happened to the perimeter?
The perimeter grew.
Okay, let's check and go to 3. Did it grow again?
Yes. It was 4, then 6, now 8. There's a pattern. Now it's 10.
Good. What are you seeing? What is the pattern?
The pattern, each time that you expand the length, it doesn't just change. As you change the length by 1, it's changing the perimeter by 2.
Awesome. So let's bring the length back to 1 and let's check out the width. I'm going to do the same thing. We're going to press that. Do you see any similarities?
Yes, the same routine. When you change the width by 1, it's changing perimeter by 2.
Awesome. So then I'd have the students talk about, the perimeter being the outside, and they could actually expand this a little bit more to kind of see how the perimeter changes when you add length. And then I'd have them actually count the outside lines here so they could see or justify that, yes, the perimeter is 26 units. Thank you. So I want to, with my students, look at perimeter, but then I also want to look at this measurement. Johnny, what's different here?
Well, I can tell you what's the same. Everything is the same, except I don't see perimeter. I now see area, and I see U squared, units squared with area.
And why do you think that is?
That is counting. I think that's going to be a count of how many blue squares that you have. And I see 1 blue square, and it is a square. Whatever the unit is, it's that one of those squared.
Okay, so let's test your theory here. If I add length, what is that doing to the area?
Oh, do that again. When you change the length by 1, it's only changing the area by 1, but 1 square unit.
Right. So now let's look, if I add 1 to the width, what did that do?
Okay. You add 1 to the width.
What did that do to our area? So let's go back.
Okay.
And then add 1 to the width.
Whoa, it doubled the 7 square units to 14. It gave us another row of squares.
Right. And so if I add another row, what is that doing to the area?
Now we have 21 blue squares.
Exactly. So then the students once again could manipulate the length and width to see how the area changes and the relationships there. Then the last thing I would do with them is look at them together. So on this last screen, we have the grid, we have our length and our width, we have our perimeter and our area. So I would ask the students to manipulate the length and width to see how the perimeter and area change in relation to each other. And one thing that I would challenge my students to do is to see if they could find a length and width where the perimeter and the area have the same number. So Johnny, if I'm going off of what we talked about and our length, and you can see how the area is just increasing 1 with the length and the perimeter is increasing by 2. But then if I increase the width a couple here, you can see, oh, that changed the area to 9. Do you have a guess on what the length and width might need to be where the number in the perimeter and the number in the area are the same?
I've been looking at area perimeter, and the 2 numbers are getting closer to each other, 9 and 12. Expand again. Let's go the other way. Whoa.
So Johnny, are those the same?
Oh, thank you. This is such a common mistake at a high school level that students see those and think, I have the same value. And yet, let's talk about the 16 units for perimeter. If we start at the bottom left point in the blue diagram And if we have a little creature who is walking that path, that creature would walk up 4 units, left to right at the top 4, down 4, and back to the starting place 4. That creature would walk 16 units walking that path. And while walking that path, you could see inside the path something totally different. There are 16 squares inside it. So even at my level of high school, students forget about units. The importance here of those units, even though we see the 16 and we think, gee, that's the same, the units tell us that we're in 2 different stories here.
Excellent. Thank you. That is a perfect explanation. And once again, by using this technology, the students have the ability to manipulate the length and width quickly so that they can see how the perimeter and area change. So that is another reason why I really like to use this technology with my elementary students. Now, Johnny, I'm going to send it back to you so that you can talk to us a little bit about how this looks at the high school level.
All right, and I'm going to start with, I'm going to first start with some middle school, and let's see if
Excellent.
I can effectively share my screen again. And how is that?
That looks great. I'm seeing what looks like might be a net.
Yes, that's a net. One of the things we wanted to do with, we've come up from elementary school learning about length and width and doing calculations. And then somewhere in middle school, we get these solid objects. And we're asked to find volume and not just perimeter or area. And we're asked to find surface area. In order to be able, for students to be able to do those things, one of the challenges is if you cut a cylinder, a closed cylinder, top and bottom, if you remove the top and bottom or cut them off and then cut through the cylinder and flatten it out, you have something that would look similar to what we have here. And this is an interactive cylinder net. So it's a 2D, 2-dimensional net for a 3-dimensional object. And with the red circle, if I change its radius, you can see it changes the cylinder size. Likewise, if we grab this point, we can shorten or lengthen the cylinder. So one of the questions that we have for students is, what is the volume of this cylinder? And the students would then need to think about a formula, and I'm going to insert the formula. Let's see, I'm going to try volume for a cylinder equals, volume would need to be the area of its base, which is pi, multiplied by, and I'm just going to use r squared. So that's the area of the base, but I also need to multiply by the height. So we can talk about that formula, but if I want to calculate with that formula, what do I need? I need a height. That number's the height of the cylinder. I need a radius. I don't have it. I don't have it. There's 2 ways to find the radius. One is to calculate, and the other is to take advantage of the technology and simply measure the length by tapping on the center of the circle and a point on the circle. And that's the radius. And I'm going to give that, I'm going to abbreviate it. And notice that's a stored variable because it's a darkened value. So let's get back to measuring volume. I'm going to remove that and simply say volume is found by multiplying pi by the radius square and the height. Just as we did before, we're going to right click and choose calculate. Now we're asked on screen to click on a number that will be the value for H. We'll choose this one. And now we want to calculate with an R value. And I'll use this value for radius. Before I do it, keep this in mind. This is not taking away the student's opportunity to skill with arithmetic. Because what we're doing here is working on a concept. And we don't want the arithmetic to be in the way of finding a conceptual answer and understanding the volume of the cylinder. Now, because of the way I did that, we have 49.3. But 49.3 puppies, 49.3 centimeters, it's volume. And let's look at that formula. H, height, is measured in centimeters. Radius is measured in centimeters, and it was measured and used twice. So we have centimeters multiplied by centimeters, and we have a volume that makes sense. In this case, 49.3 centimeters. Now, if we had an application where we might say to the students, I want you to use we have an object that fits into 100 cubic centimeters. We want you to make use the smallest amount of product to create that cylinder. So we've got to think about surface area and volume, and then we'd be able to manipulate and explore. Now, that's not very scientific at doing that. There are many strategies that are much better, but we want students to get involved with exploring and not looking for a right answer, but wonderful methods. And I think it's time for me to leave the rest of that for anyone to either write to us or explore on their own. Thanks, Lindsay.
Yes, thanks, Johnny. I like how we talked about the units and then the perimeter being units and the area being units squared and the volume being units cubed or cubic units. So once again, it's just showing how these measurement concepts are spanning the grade levels. So we want to thank you for joining us this evening. We really appreciate it and hope that you've seen how these measurement concepts have grown across the grade levels and have built on one another as the students would age in progression of education. So we appreciate everything and have a good evening.
Good night.